Hi, everyone. Welcome along to the talk. Thanks for coming along. What I want to try and achieve with this talk is to dive into what happens with analog modeling and in the kind of easiest to understand way, and try and open up the area to give access to people that may be, not able to have the confidence to do it previously, and also to talk about, just to shed some light on some of the terminology in the area and just try and make it all really approachable. So we're going to be, having a look at something like this, which is a circuit, and then turning that into code. And I want to try and keep it all pretty visual as well. And the aim is to look at white box modeling methods. So in other words, the ones that are based on components, and you stitch them all together and then model the interaction of them, as opposed to black box, which is, you're not looking inside. We want to focus on nodal analysis, or modified nodal analysis, which are pretty much the same thing, because this is the easiest one to understand. And most of the other methods actually still rely on this a bit. We want to run through the terminology, use diagrams wherever possible, and importantly, right at the end as well, I've got a whole list of references and ways to gather more information. All of these kind of areas, some of them are kind of more active research than others, but a lot of the maths has been around for a long time for this kind of solving. And I'm going to run through pretty quickly. So don't be alarmed if you didn't quite pick something up, because the slides will be available, and hopefully we can you can go through it at your own pace a little bit easily, but I want to leave time for questions. All right, now, one thing about analog modeling is it sounds good, and I think people generally agree. And when I'm saying analog modeling, I mean continuous domain modeling. So we're trying to model the structure of the circuit and then kind of discretize it, turn it into code which runs it, but keeps all the desirable properties. And this little image here is when I'm doing some modeling, I always like to do plots and kind of inspect the state of the circuit. And this one is actually a filter sweep of a Moog model, the one done by Antti, but not his implementation, just like a more modern one. But it's just the patterns and everything that come out sound as good. They look as good as it sounds. So let's give a quick, I've already touched on that a little bit, but here's an overview of what we'll do. So we'll have a quick look at the problem domain, jump straight into an example. I think examples are the best way to get because if I start talking about, oh, this is called that, and jump into the terminology and definitions, then I'm going to lose everyone. So an example we can deal with, and we'll work through plenty of examples. The examples I have mostly fully worked, except for little bits where the actual system of equations, sometimes I'll let you solve that bit. So I've just left one little bit out so that you can just do that bit, and you have to get your hands a bit dirty. So we'll run through some system formulations and how to discretize the circuit, and then talk about efficiency, aliasing, automating the process, and then I'll run through the links, and we'll have time for Q&A. So here's the problem domain. We've got some desirable analog circuit, and you know what, there's a lot of great sounding circuits, and there's a lot of engineering effort that's gone into these. So hats off to all the analog engineers. I really respect the brilliance of their designs and how good they sound. In this particular case, we've got a picture of a Korg MS-20, and there's the schematic for the MS-20. And we're going to be largely dealing with the schematic, that middle step. So we're not going to capture from the analog circuit to the schematic. We'll just kind of start with the schematic, and then try and get from that, we'll try and turn that into actual code that runs and generates audio. Right, now, although, analog modeling, we've done a good job in lots of ways for how good it's starting to sound. There's a whole bunch that is just in the too hard basket. And some things, I think heat modeling is this is what we're not going to handle. Heat modeling is one of those things which, like if you have two components next to each other, they'll heat each other up. And this is actually used in circuits for temperature stabilization and a bunch of stuff. Not many things handle heat modeling, even the commercial circuit simulators. It's a kind of an ongoing area of research. Noise modeling is handled a bit better, but we won't cover that today. So the interaction between components based on where they are in the circuit and any kind of interference or electromechanical or electrochemical modeling is we'll just stick to the kind of the easy stuff to tackle to get you into it. But I just wanted to mention that with this stuff, it goes deep. I think in audio where you can get a long way, you can get good results without having to go too deep like this. So what do we want to handle then? So we want to handle highly parametric circuits with smooth control. So in other words, knobs, like we saw in that synth, you turn the knob, it does something which sounds cool. All right. So that's the parametric. It changes the circuit based on our interaction. We're playing this instrument or, turning the knobs to do something. And that's a big part of what we need to cover. Highly nonlinear circuits. So most of these good sounding circuits sound good because they have very specific nonlinearities and they are pleasing to the ear, and we want to capture that. It helps to get the sound of the circuit if we preserve the structure and nature, in other words, where the components are laid out, how they're connected. And then we want to also, it's a desirable thing to be able to handle component variation. So when a circuit's manufactured, each circuit is slightly different to the other, and you want to be able to capture that as well so that you can kind of roll the dice on a new circuit and you get that natural variation. And that's, I think, a big area that is being tackled by a few companies, and it's used in circuit design a lot. The circuit simulators allow you to do this, they call it Monte Carlo analysis, and that's exactly it. You're rolling the dice, seeing what the circuit does, making sure it falls within specification. We'll handle energy storage components, but not too in-depth. And we want low CPU and low memory usage and low aliasing. So it's a big list of conflicting things that we want to handle, because all of that highly parametric, highly nonlinear, preserve the structure, component variation, all that stuff doesn't go well with low CPU and memory usage. And that's like something that we need to try and tackle as well. So we'll look into methods of doing that. Okay, so let's jump into the first example. And I am a fan of drawing and, getting a piece of paper and pencil and just working through from first principles, because then I understand it. I find a lot of matrix equations and papers slightly impenetrable. And until I do a little example, I don't really get a feel for it. So let's start with our first example, a diode clipper. And this is the classic circuit, which is simple enough that it's approachable, but complicated enough that it exhibits a lot of the problem domain. And to solve this kind of thing, we only need some basic line maths. So I'll run through what that means. So linear equations, in other words, and linear algebra is the actual term, but let's just, that sounds scary to some people. Let's call it line maths. So everyone hopefully is comfortable enough that we can have a parametric equation for a line, which is just y equals mx plus b. So we have some slope that we scale and some offset, and that's our line. And the linear algebra side of things is just really, let's solve that equation. So I'll just jump in with a little pointer. So that's our starting point, and we need to solve for this x. And so we come down here and x equals, we just do the opposite. So first we subtract the b, then we divide by m, and there's our solution. If m not equal to 0, which that's that classic thing. As soon as m is near 0, then everything does not bode well for the accuracy of our solution. And that's something to keep in mind. And that doesn't go away with no matter how many, you stack more and more, it can just kind of be hidden, but it's definitely something we need to keep an eye on. Now, the next bit of the linear maths is turning some curve into a line, because all of the solution to all this stuff, we can't really solve we can't use the original functions. We basically have to turn everything into a line, and then we can solve it like we just saw in the previous slide. So what do? We take some, so there's our line that we want. So how do we get this line? Well, we need some M and we need some B. So the M normally is some approximation to the slope here of the line. And the B is just where we hit here when X is 0. So we just draw that line, boom, there it is, there's our B. All right, so pretty straightforward, and it is when you're actually doing it as well. It's literally there, so we got some estimate, we have our function value, and then we take away from the function value the slope times the X that we're at, and we're back to the B, so we've got our B. All right, so, this is back to that circuit again. So the reason that this circuit is also good is because we've got 2 bits to it. So we've got some filters which have some memory, and they do, high and low pass filtering. And then we've got this nonlinear bit, which has no capacitors, there's no memory. So we're going to tackle this one first. And we need to bring in now, I think, I'm not sure of the exact pronunciation of Kirchhoff, but I've always said it like that, so sorry if that's wrong. So we need to bring in Kirchhoff's current law, and he's a German mathematician, German physicist that kind of preceded Maxwell, and but it's a similar idea. It's this sum of around something equals 0. So in terms of understanding Kirchhoff's current law, it's easiest to think about, so we'll come down here, it's easiest to think about water. So water comes in and in a pipe, and then the pipe splits into 2, and the water has to go somewhere. You can't have more water come in than went out, or go out than came in. The same amount has to come in as comes out. And then you can write this as some symbols down here. And the important thing to note here is that when you're dealing with circuits, you've got 2 numbers. There's the current and the voltage. And this is the real world analogy. You still have a current, which is the kind of flow of water, but the voltage is the pressure of the water. And these are physical things that you get, which are natural with water, that I think when you're into DSP, you're stuck with the V. You've got the signal, and you're processing on that, but you kind of forget about the current. You've kind of split apart. You've made it, you've separated those 2. And in circuit modeling, you don't separate them. One leads to the other. And this is this kind of trade-off and gentleness that you get when you're modeling, in this case, not such a physical system, but the electrical system. You don't get something for nothing. There's always little bends and trade-offs and things, which sound good. So we are going to, I just kind of cheated a little bit on that last one, because it's not actually just the addition of these. These fellas have a direction. One points up, one points down. It's pretty clear. There's an arrow that's there for a reason in that symbol. And what happens is that these diodes clip the voltage coming in. So they take the top and bottom off a bit, and that is the equation. Now, there's a little plus and minus to show you the direction, and that's where they come up here. So don't worry, this is starting to look a bit more complicated, but these are all straightforward equations, and now we've just turned that previous slide into the equations for a resistor, and the exponential equation for a diode, a basic model of those 2 things. So that's that one and that one. So they plug together, and you end up with this, which is the important bit. So this is the equation that we need to solve. So we need to work out where that equals 0, or where these 2 bits intersect. They're the same kind of thing, and it's V2 is what we want, the output voltage, but it's up here inside the exponential function, and it's up here inside this one, and we can't solve that. This is called an implicit equation in V2, and implicit equation solving is where it's at. That's where a lot of what we're doing is this nonlinear implicit equation solving. Okay, so how do we do that? Well, we need to go back to our lines. We need to, so there's the solution of the zero and where the line and those curves intersect, and that's what we want. We want to work out where that intersection is. So how do we do this? We turn it into a line because that's all we can solve. We are not good at solving anything more than lines, which is kind of slightly depressing in this day and age, but lines it is, and they work, and here we are. So linearize, so we have our equation for the diode, and then this is the derivative of the exponential function. And then we do that little thing that we did before, which is we take the function value minus the slope times the voltage, and that's our B, our offset. So this is our M, this is our B, and we get this one here. So our diode current, I for current, diode equals some slope times the voltage plus some other term. And that's our line. Great. So we plug that in instead. Now, if you see what's going on, we've taken that equation, which was the straightforward one from the circuit, we plug in our linearized diodes, and now we can solve it. Yippee, we got it. And this is the one solution that I'm going to give you. The rest, I'll just leave it like this, and you can solve for these bits. But there it is. And now what does that do? And so here's the pseudocode for that. Now these are just some constants. They can be whatever. Everything's a number in solving, but they're kind of, you can change those. That's some of that component variation. And then in here is the exponential, the derivative, and forming the y equals mx plus b stuff, and then solve using that equation that I just showed you. Okay, and more importantly, what does it look like? Well, that's a wave shaper. It's a memoryless nonlinearity. And it looks like the top slide there, and chops off the top and bottom. Now, actually, can I go back one slide? Yeah. So in this one, you notice I did this, V2 equals 0. So we have to have a starting guess for what our answer is. And 0 isn't the best guess, but it works. We get there, but unfortunately, when we tick this, what happens is, I missed this bit as well, when we linearize the nonlinear equation, we need to iterate to work out where the 0 is. So we have a guess and we go down to where the 0 is, and this is called a Newton-Raphson loop, and that's what that is. And we execute this a number of times from a starting position, and we converge to the solution. And this, unfortunately, took 50 loops. And obviously, that's 50 times 2 exponential evaluations, not good. Right. So 0 was not the best guess, but it works. So let's move on. So this is what it looks like when you clip a sawtooth. So I'll give these examples for all the circuits. And we're done on that one because we solved that circuit. So great, first one done. We've covered implicit nonlinearities. Now let's do memory filters, in other words. So this, again, it starts, I'm sorry that I can't write it in a more pictorial way, but I will soon. A capacitor is something which integrates current. So you give it some current and it adds it up, plus equals the current. Or another way to write that is that the derivative of the voltage of the capacitor is the current. So they're, basically the same thing. I think this is probably a bit more computer friendly. The voltage plus equals the current. All right. But in the literature, we have to deal with more this form. So I'm going to do it in this form because otherwise you'll get lost. As soon as you look somewhere else, you'll see this. So we're dealing with this. So F here this is our F, and our Y is our voltage over the capacitor. So that's what we're trying to get. What is that voltage over the capacitor? Okay, so remember our F of t is the current of the capacitor. Y is the total area under the curve. So we're adding up, we're integrating that area, and that's the voltage of the capacitor. So we just add up little bits. We take a starting bit, initial, and then add on a little chunk, add on a chunk, add on a chunk. Okay, so that's basically what is happening. And then things get a bit messy when you start writing all down the actual equations for all this stuff. So this is the messy bit, sure. So you're adding on little chunks of your F function, and you've got some weight that you add on. And these are all called different names: backward Euler, trapezoidal, BDF, Adams-Moulton. But this is the general kind of form of what's called linear multi-step methods. Okay, so let's just break one down. Trapezoidal, what do? Well, we are taking half the height value between these 2 points, so which is this level. So half of this function, half of this one, and then we multiply it by the width, and we've got that area to add on. And that's it. So actually pretty straightforward. Looks a bit scary there. But you notice in that one, well, I mean, why did we take the half value? Well, there are some good reasons for that, but it's not the only option. We could take any weighted value from 0 to 1, crossfade the values, and at the bottom we would have forward Euler, in the middle we'd have trapezoidal, and at the end we'd have backward Euler. And backward Euler is just has different properties. This one is the one that mostly we will be using, because for filters it does some nice stuff for us. There is another one which is quite interesting, and that's the midpoint method, which gives you, if your function was a straight line between here and here, then it gives you the same thing as trapezoidal. But for nonlinear evaluations, it gives you a slightly different answer, but a good one. So this is called the implicit midpoint method. And yeah, so that answer quickly is here. There's your function values here and here, but they're in the points that you're evaluating the function are inside the tan H, but this one has like an average, the midpoint one. So you can see that they're different. They'll give you a different answer. And this is quite good because you're averaging, which is kind of a low pass filter, and then you apply the nonlinearity. So that, in a sense, can give you a smoother result. All right, so let's get back to the voltage over the capacitor. We have that's what we were dealing with, our Y's and F's, but let's just give it voltage over the capacitor and the capacitance and the current. So we need to solve for these. We stick that into our nodal equations. So how do we do that? Well, first of all, let's break that all down, so we have to substitute into, this was the formula that we had for trapezoidal. So that's the scary one. And hopefully, and it doesn't get actually any much scarier. That looks pretty messy too. And we're doing this for the mix version. So we can mix smoothly between trapezoidal, forward Euler, and backward Euler with that M term here, here, and here. So that would just be a half if for trapezoidal. But it's nice just to see it in full, because I want to give you context because there's many different methods and they have different weights, and this introduces some weights instead of just whacking in a half and then you only ever see 2s everywhere. All right, so we need to update our state as well based on the solution to the linearized set of equations. Then we need to add on, do that plus equals bit to actually add on to the state. And there is, notice this negative term, and that just makes things nicer. So when you're looking through these examples, a lot of the time in SPICE kind of literature or something, they will not have a negative here, they'll have a positive, but this just is better for circuit modeling to do with other kind of the plus equals side of things, which makes things look a bit nicer. So here is our state update. So we started off, that is just our linearized term for the capacitor, which includes this lumped all our past memory and this thing that we're solving for now. and it's y equals mx plus b again. We're back to a line, but sorry, this is the state update. So this is the kind of past, and we need to update it to the next time step here, and it ends up being like that. So I'll let you work through all that. You can look at the slides. Let's move on. So we have our linearized capacitors. Here they are GC1. So G, remember, is the slope of the capacitor, and our voltage over the capacitor, and that's our memory bit. And then we've got it appearing here as well. So we're just going through. So at node V2, we have the negative of the first capacitor and the positive of the resistor. And then here we have the positive of the first capacitor, the positive of the second capacitor, and the positive of this resistor. That's our Kirchhoff's nodal equations, and we can solve that, right? Because that's all lines were good. We can do that. So in terms of actual circuits, this little bit, just to let you know, that little y equals mx plus b bit that we turned the capacitor into kind of looks like a little resistor and a little current source. So remember, we're in the kind of the current land, and we're adding up currents and we're making them all sum to 0. And that's what it looks like if you drew each little thing as its own little component. All right. And there's the solution for that as well. I gave you 2 solutions. I wasn't meant to do that. There we go. And there's the pseudocode for it. And here's our state update. And there's our plus equals on the values of the voltage over the capacitor that we worked out. And what does that look like? Well, there it is. So we got some low pass filtering of this sharp edge, and then with this straight edge kind of bows backwards, so we've got some high pass filtering. Okay, so there we go. Now we need to put it together for the nonlinear and the memory. So I'm going to skip through a little bit because it's the same kind of thing. So we just put together exactly the same linearized equations that we had before, but now we got the diodes in there as well. And pardon me, here are the diodes, and here's the diode. So they appear at this terminal V3, and we have our 2 equations in 2 unknowns. We know what the input voltage is. 2 equations in 2 unknowns. We can solve that. We can do lines. There's the equivalent circuits if you want to draw them in full. And here is the pseudocode. So this is, remember, this M is for trapezoidal, that half. And there is the code. So we've got our exponentials, our derivatives of exponentials to form our y equals mx plus b. We solve using those equations that I just showed you, and then we increment the states. And that gives us that. We run that circuit and we get this clipping, but we get low pass filtering and high pass filtering and clipping all at once, which is great because that sounds good. Now, there are easier ways to do this. We could just filter and then clip. And the blue is that. And you see that the full model looks different and it sounds different. And especially this bit here, that's a sharp edge, and this is smooth and rounded. And same up here. And that is what happens when the signal is quite loud. When the signal is quieter, you get more like the blue. It's quite dynamic. The sound that you get through not buffering and separating in a traditional DSP way, the nonlinear bit from the linear bit, from the filtering bit, if you put them both together, you get these kind of dynamics which sound great to the human ear, and that's why we like analog models, because they sound good. So when you play quietly, it's a bit duller, and then you hit the guitar hard or the synth, whatever that you want, then you get this brighter, this dynamics, and that's really desirable. So we just ran through a whole bunch of stuff there when we've solved our circuits, and there's code that you can break down and have a look through and get your hands dirty and start working out the solution of those linear equations and actually get some results. So what we have covered the numeric integration of nonlinear differential equations. That's the scary terminology I did not want to start with. And we have discretized the continuous circuit. So we've sampled that continuous equations at a constant sample rate. That's our 1 plus equals, and we have that sample rate, which if you look back in the code examples, you'll see the sample rate in there. We have solved implicit nonlinear differential equations, and we needed to iterate to a solution to do that. There's a little NR loop bit. And that means we get a new output from nonlinear equations of new state and new inputs. In other words, we're solving for the state in terms of itself, which is, that's the implicit bit of the numerical integration. And then there's the implicit bit of the nonlinear side, and they're both called implicit, but one of them, when they're linear, we can solve for it. We can do our y equals mx plus b solution for x, but when they're nonlinear, we have to iterate to a solution. Implicit linear differential equations, we can do in a single step. And explicit differential equations, which is like a Chamberlain SVF, is a single step as well, but we don't get quite the same answer, and we do get trouble with stability and things. We can get trouble with stability, of course, with doing full iterative solvers as well. So let's have a look at these things, the ways of solving implicit nonlinear differential equations. One of the big categories of these things is called rung-cutter methods. And here is a list of those from Wikipedia. And we covered this one, the mixing version of this one, trapezoidal. And there's the implicit midpoint one, which I didn't show you in detail, but I quickly showed you. Forward Euler, which nobody really uses. And this is another one which can be used a bit, which I want to quickly touch on here. And this is called rung-cutter 4. But there's a lot of them. You see, we're in our little audio world. Hi, we're up here. All right, maybe a little bit over here. A bit over here previously, but we're moving towards this. But yeah, just to give you some context, there's a lot of this stuff. And you'll be seeing these things. So probably we'll just concentrate on this one where we have that half. We have half of the function value at one point, half of the other, and then this is a bit different because in what I've showed you, we just only had that. This is the kind of output weights as well, which you don't have to have the same weights, but in what we did have the same weights. So in explicit rung-cutter 4, here's our function that we're evaluating, which is possibly nonlinear, and this is an explicit method because you see down the diagonal, they're all zeros. And if we look back here, down this diagonal, we had a number. And here, we got a number. And there is only one diagonal, we have a number. That means it's implicit. We're solving at the current time point in terms of itself. Here, it's explicit. We don't need to have the solution here. So this is we can do this without this implicit iterative solving. But we need 1, 2, 3, 4 function evaluations of the nonlinearities. And then we do a big sum to get our answer at the end. So don't worry about that too much. I just wanted to show you some context. Now, we solved the mixing version, and I just wanted to show you what that looks like in terms of the frequency domain. So if we do a plot of a one-pole low-pass filter, solved with trapezoidal from the bottom, this one here is trapezoidal, and as we change that M term from half to 1, this is kind of what happens. We go up here, and this yellow one is the continuous domain curve that we kind of desire. So I'm just showing you that we can get closer to the continuous domain one just by varying this mix parameter, which we didn't even have to do anything else. We just varied our numeric integration a little bit. So that is, we're going to plow on. And so sorry if this is going a bit quick, but I just want to cover a lot of material and leave time for questions. Let's talk about system formulation and discretization. So we touched on this a bit. So normally for audio, we're dealing with second order methods. They're enough, and the ones that we're talking with are mainly the second order linear multi-step. Now the linear multi-step, I don't mean they're solving linear equations. It means that it's a linear weighting that of the terms, of the nonlinear terms. Another one, which is quite good, is developed by Gil Strang at MIT and someone else, sorry, I can't remember their name, is called TR-BDF2, which is a really good method that I think deserves, and it's applicable in audio. You can actually use that one for a lot of stuff in audio, and it's pretty cool. And I'll just mention it so that you've got further things to look into. Run Cutter 4 is actually used quite a bit in the audio community, I know, in quite a few products. It is, and gives decent results, so it's worth just having a play with it and see if that's good enough for what you want. But normally, we don't go above second order methods because we're better off oversampling, because that helps contain our harmonics as well as get rid of some warping, and we spend the extra CPU there instead, and then that makes our life a bit easier when we push up against the Nyquist limit and all the equations fall apart a bit. So now this is a big one actually. In what I've showed you, I've used the same integration method on all the components, but you can use different ones. You can break it up however you want. It doesn't matter. Sometimes you want to match the phase for a filter, and you use trapezoidal. Sometimes you want to match, it's just a tone filter, and you want to match the Nyquist gain. So then you might use that mixing filter that I showed you. And you can change which one you use on whichever component you want. So the formulations, what are the different formulations that we can do? We have shown this one, nodal Kirchhoff's current law, which is MNA, modified nodal analysis. And the modified bit just means we solve for some currents as well as some voltages. So normally when you have at the nodal equations solve for the voltages, but in modified nodal analysis, you can also solve for some currents. And this normally comes in when you have voltage sources and you need to chuck them into the equations in a consistent way that makes it so that you can automate it. But you can do loop-based, used Kirchhoff's voltage laws, where the sum around loops of the circuit equals 0. There are state space methods, wave digital filtering, which has been covered on one of the other talks a little bit, and this gives you a traveling wave formulation, and it's kind of like a finite difference method, and you'll take your current and your voltage and your current, and you add them as the transmitted wave, and then your voltage and your current, and you subtract them for the reflected wave. And that's I do like that method, and I really hope that there can be some more progress made on it. It's quite interesting. Now, other formulation options, when we had to iterate, that took a lot of CPU. So if we want to get away, you want to pre-compute something, then we do the discrete DK method, discrete Kirchhoff's method, which is called in nodal or state space, and it's called the DK method. And I'm working on another method called the PDK method, the parallel DK method. All right, so the state space is something that we will cover. We're not going to really cover wave digital filtering, but let's get into our second example to show the difference between nodal and state space, basically, and some of the problems that come up when your circuit gets a bit bigger. So this is a highly parametric circuit. This is a Salin key filter. This is the filter that's in the type of filter that's in the MS-20 that I showed at the start. And we have our cutoff frequency, which is a gain here. These guys output a current. They take a voltage difference here and output a current to the capacitor. And this section is a one-pole low-pass filter. This is a one-pole low-pass filter, but it has some feedback coming down the bottom leg here instead of just going to ground. So this gives our resonance. Okay, so we form our linear equations at the nodes. And in this one, that's just the straightforward ones that we've done. And there they are. The G is the gain made by this one here, and there's the voltage difference, and that's the current that comes in. Don't worry about the signs. They all work out. You can go into that in more detail later. This is the interesting one, the difference between these two. Now, in state space, you model over the capacitor, the voltage over the capacitor. And you have to formulate up in here, instead of V1 and V2, probably, so on this capacitor is the best one to look at. So it's probably, so you were forming this, but now on this one, we have a different term here, and you have to kind of follow up and around and then up. So you have ground, you add on VC2, the voltage over that capacitor. This is a buffer that comes out, so it's just giving that same signal. You multiply that by K, the resonance gain. Then you add on your VC1, and then you're at this voltage here, which is all of, and then you take, and that's the one that gets subtracted. So this is where, so V1, subtract all that stuff. And so you can see that's a quite different formulation. And state space gives you the same answer, but it's just numerically different. It has different properties. And to do state space solving, we're going to take this second term and we're going to transform it into the voltage over the capacitor. And then we do that, we make that substitution, and we solve for the dVC1, so that's the delta of VC1. And we get a different state update. I'm just going to skip over these. You can go into more detail. And we get this kind of a state update. So that plus equals on our state of the difference. So we've already calculated that current over the capacitor, which we're going to add on. So that's quite nice. And here it is in practice. So this is the nodal. And you can see really the only difference is the equations here that we solve for, and then the way that the state is updated. Here we solve for the voltages directly. Here we're solving for the voltage over the capacitor. Then we use those to get the nodal voltages. And then we have a slightly different state update. But they give you the same answer. There's the two on top of each other. You can't tell the difference. Okay, so let's now look at what happens if these were all nonlinearities. We just solved the linear version of that. But when they're all nonlinearities, things get messy, and so that's a lot more complicated. But we come back to this a model program because it's a bit more straightforward. I can show you what decay solving is. You turn these ones, the currents over the exponential terms, just leave them as a single kind of term that we can substitute in and mess around with. And so they add some current, and that is the nonlinear contribution. And then all this stuff is the linear stuff. So to do the decay method, we solve for the linear contributions, work out a voltage offset that those linear contributions, VDK1, this is the voltage offset, into our nonlinear terms. So work out what the linear contributions are and how they change to make the nonlinear contributions. So sorry, I'm having to go a bit faster so we can fit in some questions. So we solve using the computed nonlinear contribution for the final result. And then we use that to, so we just add on those terms that we solved for. And we've split apart our nonlinear and linear contributions, and our nonlinear contribution only depended on this VDK1, these linear contributions, not on the capacitor values. We kind of lumped them all together and got a single number, and then we could take away all the contributions from the linear stuff and the nonlinear stuff. And it's probably easiest just to see that in code. And so this is the init, which looks the same as our other one. And here we go. So we solve using for the linear contributions, and then we calculate our VDK, which is V3 minus 0 in this case. And then we stick that in here into this function can be any kind of, you can pre-compute this. This is the good bit. This is the pre-compute. You get your two currents for the diodes back out. You add those ones back on in the, and you get your answer, and you're out of there. So this is the bit that's important, and this is the decay table bit. This is our offset. We're solving still for V2 and V3 like we did before. And we've offset this one here and this one here. And the important thing to note is in these equations, when we did this substitution, there was no V1, there was no IC1 equivalent or IC2 equivalent. So we just distilled them all into this one parameter which we can pass in. So this is called a And there we go. Are they the same? Yes, we're all good. They are the same. The blue one you can't even see. Now, what did that table look like that we just computed? That function, that dk table function, and there it is. And in 2 dimensions, so just say we had 2 nonlinearities that interacted with each other, then it would look more like this. And the good thing about this is that we don't have to iterate. We can just look it up. So let's jump back to the harder case. We have 1, 2, 3, 4, 5, 6, G, and 7, K. They're gains that change how the circuit behaves. So that's 7 inputs. We have each of these nonlinearities has an output. So that's 5 outputs. So this means we have a 7-dimensional table, and it has each point in the table has 5 numbers. So what kind of a table size is this if we want to pre-compute it? Well, if we had 128 in each dimension, then unfortunately we get around 5 petabytes. Even 16 points, which is really not much, we get 5 gigabytes. So obviously that's not good. Pre-computation is good, but we can't always do it. So solving efficiency, we can iterate and pre-compute a bit. The MIMO multiple input output table sizes increase exponentially with the number of parameters and nonlinearities. You can throw neural networks at the problem, which is great. So this is where they come in. You have this MIMO table and you need some approximation for it. But I mean, then you have to worry about how smooth is that function. How accurately are you doing it? Can you vary the components? And then you have to train another neural network. And then you've got basically taken a snapshot of one particular circuit, which maybe that's a good thing. Maybe you want to have other aims. Ideally, we want to split apart the nonlinearities. So we can have, instead of the table size to the power n, we want the table size times n. And this is what I'm working on with this method that hopefully I'll publish a paper on soon. And we can split the circuit into sub-chunks and iterate a bit on those. And I think that's kind of reasonable middle ground. But in one of my recent products, I actually am just doing brute force, optimized full brute force iterative solving because it turns out to be cheaper most of the time. Worst case, PDK is better, but most of the time I'm worried about the most of the time. Keep it as low as possible. All right, so let's have a look at how much time we got. Yeah, we got a little bit more. So let's have a quick look at aliasing and what can be done there. Now, the good news is solving these equations and having circuits that already sound good typically sound good because they kind of bend in pleasing ways, so they're not too harsh sounding, and that already gives us lower aliasing in the first place. And we've got control over the smoothness of our functions. So when we saw that table that just kind of went along and then went up, we don't have to have that DK table exactly like that. We could make it even smoother if we wanted. And so we can lower the aliasing. But when you do any numeric approximations, it's always good to match the derivatives at the endpoints and to keep it as smooth as possible. And then that helps with lowering your aliasing. There is another method which is really cool called anti-derivative anti-aliasing, and it adds a half sample of delay. But Julian Parker and guys at Native Instruments saw a really cool thing, which is that you can roll this half delay into the trapezoidal integrator, which already gives you a half sample of delay and mitigate the fact that this happens. And so that's actually really cool, but only applicable in some situations. Oversampling helps as well, because you get better phase response as well as aliasing. And even better, if you can, offline rendering, so you can get even more anti-aliasing. So it's important. So Anna had a talk earlier on kind of iteration and things, and I think it's important to try and have quick results when you're doing this stuff. And when you're solving big circuits, So this is actually the screen, the matrix. When you formulate those linear equations, instead of just writing them all out, if you can form a matrix from them. And this is what it looks like. And it's kind of big and kind of scary, and you want to automate that. And then you just let the computer do the crunching, and then you get to play with the sound straight away. So being able to automate the process means you can handle larger and more complicated circuits. Faster iteration means you can try out new ideas and see what works in context. Now, what I am an advocate of is code generation. So I have something which turns those equations into a C++ class, a templated class, and then I can compile that and run it and have quick turnaround. And that also is handy because then if you improve your solver in some way, you can just crunch over the circuit definitions that you already had and get a better solution and roll it out in your products. And it took, only a few minutes. It's also handy with code generation because you can target different programming languages, but you have the same high-level specification of your circuit, and you can just go, okay, I'll output to Python, output to C++, output to Mathematica. And it's more upfront work, but it does reduce errors and saves you a lot in the long run. And the other thing which is kind of cool with circuit generation and automating the process is you can have different levels of detail. So all those nonlinearities that we included, you can take them back out and then have lower CPU versions, because the more nonlinearities you have, the more CPU you use. Excellent. So I went through pretty quickly with all of that, and hopefully it wasn't too much, but I hopefully covered and gave everyone some confidence to actually get into this and have a go.